All right, thanks for joining the last day and last session of my presentation. So I'm Prasad Venkatachar. For today's presentation, I have a very lengthy title for the topic, Overcome Blast Radius Anxiety with Fast Rebuilds with the High Performance Capacity SSDs. So it essentially means how can you use high capacity SSDs for your database applications. So that way you don't, in the event of any failures, the impact of the performance or data or anything will be kept minimal. So that's the essence of this. Maybe since a database conference, I should have tailored this more to the database centric. So I'll take care of that next time. A little bit about myself, so I'm working in the database and analytics field for the last 20 years. Being as a DBA, started my career as a DBA manager, solution architecture, and then moved on to the product management. And as part of this career transition, I worked on several different databases and acquired some database certifications, both on the database, big data, and the cloud certification. So the company, about my company, though I work for Pliops. This is one of the fast-growing, organization. I mean, fast-growing company in the San Jose, California. And so we have an ambitious goal to massively accelerate all the database analytics and the software-defined storage applications, and at the same time lower the infrastructure cost. So that's our mission, and it's catching a lot of good traction with a lot of the hyperscale providers in the SaaS and infrastructure as a service. So I'm both in the US, China market that we are seeing a good traction. And when it comes to the enterprise customers, we are seeing a lot of in the manufacturing, retailer, and high performance segment. So with that said, as part of my presentation, the topics that I'll be discussing is the typical database deployments on DAS, direct attached storage, and software-defined storage, and the best practices for the deployment. And so we have some of the testing that we have carried out with using MySQL, MariaDB, and MongoDB. And so essentially that's it. And feel free to ask any questions, stop and ask any questions. So typically when you deploy a database, right, for your applications, so you go through a direct attached storage, right, for MySQL, MariaDB, or MongoDB. So if you use a direct attached storage, or for a distributed storage, you use any of the distributed storages, like the Ceph, Gluster, or vSAN, or any of those, which is a scale-out environment. The one thing that happens is when you lose an SSD, what happens is if you are not consider the data protection within the system, so that means the users which is connected to the application, you have 100 users, that 100 users you need to migrate over to the secondary instance. So that is where it becomes a big problem. And the second is if you imagine losing an SSD in the software-defined storage. Losing an SSD means if you have a high density capacity, let's say if you're using a 7 terabyte or 15 terabyte. So imagine the kind of the traffic that goes between east-west traffic to rebuild that amount of data set. That will be huge. That we are looking at the performance of this distributed storage is degraded to a significant level, and at the same time impacting a significant quality of service. So these are two big pain points. This is where the blast radius, that's the essence of the topic, where the blast radius means how many users get impacted, right? How many workloads gets impacted. In the software-defined storage, if you see here, I have a MySQL application impacted, MariaDB impacted, even the MongoDB. So if you have 100 users from each of these apps, 300 users getting impacted with one single failure from the SSD, and the quality of service is taking a big beating on this. So probably you would have heard about recently the Confluence, Jira, all their entire product suite was down for almost 12 days. The reason was a simple upgrades in one of their into their code base or something that impacted the significant number of users for a lot of amount of time. So this is where the blast radius comes into the picture. Like, so how many users get impacted and what workloads, how many locations. So when you are providing any of the customer facing application, this is very, very critical that you got to factor in. So another thing is like, so the database capacities are growing, and so as the big data capacities are growing, and the SSD capacity is growing. But you can't tap into those benefits to increase the density of your, how much data you can store per server, because you hit into the blast radius, right? Because the fault domain from a particular server will become so big that losing that in a server or a storage, you will have a big impact to the overall data uptake. So what you see in the graph is the capacity is from 1.9 terabyte all the way up to 15.36 terabyte. This is the high performance SSDs. So on this other axis, you see the storage density you can store per server. So as you move from 1.9 terabyte to 15.36 terabyte, you can approximately, this you can store up to 384 terabyte of capacity with a TF. So the problem with this is like once you go into 3.84 to 7 points, the performance per terabyte remains stagnant. So even you can increase the density, the performance per terabyte remains. So that means after certain density you hit the limit, you can't, if you add more applications, more users, in the event of failure, the performance will be a big impact. Even you can't scale the application and the density will take a big beating. And other challenge here is these high performance provides a good, provides a good performance, at the same time good experience for, but at the same time it is very expensive. So this is where the dollar per terabyte comes into the picture, right? Like, so if you are designing an application, so number of users supported this and also associated with how much capacity you're storing, how much you are ready to shell out, in terms of the dollar per terabyte. But the same thing on the QLC here, the capacity, the cost gets significantly lower, but at the same time, the performance reduces by half. So here you can lower your infrastructure cost or storage cost, but the performance gets impacted. So this is where we kind of come in here to help improve the performance of these QLCs. So that way it almost looks like a TLC kind of performance, but no impact to the performance. So when you're designing an application, so what are the fundamental 4 tenets of you got to look into for supporting any database application that supports any customer facing application? Performance is a number one, sustained performance. Again, this is where you have to get a consistent performance across different block sizes from 4K to all the way 16K, because different applications from MongoDB to MariaDB to MySQL comes in different block size. So you got to think about, even if you're supporting the relational database, like for example, SQL Server or Oracle, that has a different block size, that is at 8K. So there is 8K, 16K. So you got to think about, like, if my application block size increases, I have to make sure that I provide a consistent performance. The second thing is the outage. In the event of any of the outage to your infrastructure component, your goal should be the drop in performance should be so minimal that it will not impact any of your quality of performance. So the performance during any of the recovery or restore operation should be minimal. And that should conform to whatever the performance SLAs you kind of signed up with the customers. Because otherwise, if you are a cloud hosting customer, some of these things, so you got to pay for a cloud credits, because once it goes below the certain performance level, there is an SLA impact to it, which is translated to cloud credits. The third one is the data loss. Obviously you have to make sure that there is no impact on losing any kind of the infrastructure component. That way, the data loss has to be kept minimal or absolutely zero, right? So this is a recovery point objective has to be considered kept. A lot of important needs to be provided on that. And finally, the capacity and the cost. So losing any of the infrastructure component, so that means that you should not be still able to expose the same number of capacity that you have provided to the users. That way, the capacity should not go down. And the same thing is the cost, right? So overall, when you're looking at building all the components, you should make sure that this is absolutely taken care in terms of the dollar per terabyte, dollar per IOPS, All these things should be considered. So that way you are not incurring a significant cost in when designing this application. So keeping this in mind, like, we evaluated, like, setting up a MariaDB, running the Sysbench TPCC workload. For the baseline, we ran one with the RAID 0 setup where there is no data protection, and another for comparison where we enable the Pliops. The Pliops provides a built-in data protection. So the product is XTP, Extreme Data Processor. So it provides not only the performance, as the name indicates, extreme data processing means, but it also built-in data protection. So when we tested this Sysbench running the TPCC workload, comparing with the previously, okay. So comparing this with the baseline, which is a software RAID 0, which means the RAID 0 probably you are familiar, like, so it provides the best performance compared to any of the RAID configuration, but it doesn't have a data protection. So comparing that baseline, which is clocking around 50,000 QPS, queries per second using the Sysbench, and the Pliops performance is 2.5x higher. That's around 25K queries per second. So you might ask, how can I get a 2.5x higher performance where you're providing a built-in data protection? So that is where we kind of provide this. We tap into the benefits of converting all the random writes that is coming from the applications, which is, like, in this case is a MariaDB. Before it writes to an SSDs, we convert all the random writes into the sequential writes. So that way we will take all these things, aggregate it, and once for all go write to it. So that way, for example, and if you do a simple math, right? For example, a Samsung PM 983, which is it does a 50K random writes, and the sequential write is around 1 gig or something. So if you combine that into, convert that into a throughput, that 50K translates to 200 MB per second. But the sequential write is 1 gig. So that is a 5x difference between the random write to the sequential write. So we tap into the benefit of getting all the random writes from the application, that is in this case MariaDB, and convert and change that into data. We take care of all the inline data compression and data sequentialization, and all the at the same time, the next point I'm going to, in the next slide, I'll highlight about how do we minimize the data amplification. So this is the three benefits that is helping to provide a 2.5x higher performance than that of the RAID 0, which is unprotected. So those three, then we simulated at this stage, we simulated, okay, let's crash an SSD. That means pull out an SSD from the RAID Pliops storage array. So we pulled out an SSD, and we wanted to make sure that, what happens if you pull an SSD from a live working database, right? So this is where you see that the performance has come down from 125K to close to 100K. So that's around 15 to 20% of performance drop. And this is much higher. This is almost 2x higher than the baseline. So our goal is, not only provide a high performance, our objective is also to make sure that, because this is used for majority of the customers, which I'll talk about in the next subsequent slide, is used for a database application. We want to make sure that the drop in performance is kept very minimal. And we provided two knobs for the users to tune in. One is for where the rebuild happens very quickly by taking some performance hit, or we can extend the performance, rebuild duration to a longer time, but minimizing, but taking some performance hit. So depending upon what kind of an SLS, we provide those two knobs. And once the rebuild is complete, as you see here from at this stage, is the mouse pointer working? So once this rebuild process complete here, so you will get back to the sustained performance here. So this duration from this 120 minutes to this around 220 minutes, that's probably around a 2 hour. So here the rebuild per terabyte is around 25 minutes. So these are 4 terabyte, you will see around per terabyte 25 minutes per terabyte of duration, right? So, and by the way, I do have a comparison of same thing without using the RAID 5 in the follow-on slides. So here, when we go and use this to a customer in one of the large SaaS providers, they have the customer-facing applications and the data centers both in the Seattle as well as in the San Jose, California. So they have something similar scenario. They went with a design trade-off based on their the business requirements, because business and technology requirement where they wanted to provide a high performance and high resiliency, but they compromised on the capacity that they wanted to store on each node. So this is a MariaDB, a SaaS application, and behind the scenes is MariaDB, and they provide an asynchronous replication between the primary to the standby using and to take care of the recovery point and RTOs and RPOs. So when we worked with them, demonstrated how our product works. So this is where the things on the left-hand side, as you see here, losing any single SSD with a RAID 0 setup, they had to fail out all the users from the primary instance to the secondary instance. So here, what they've done very fantastically in the designing the database architecture is, because it's, as I said, it's a customer-facing application. So when you log into this application, each user gets their own dedicated MariaDB user instance. So they isolated the fault domain in the database layer, so that way any rogue user or some user making some kind of a abnormal this one will not trigger a false failover for the rest of the other customers. So that way they isolated the fault domain in the database layer. But the problem there is, for that is the storage tier, but they had to pick the RAID 0 setup, which is no data protection, because they wanted to get a higher performance that meets the SLS. So they have a very good design aspect on the database tier, but on the storage tier, they had the issues because of the RAID 0, which has to meet the performance SLA goals. So this is where we come in. So where we demonstrated to show that so you don't need to trigger, there is no need for any of the failures from the primary to the secondary environment in the event of losing an SSD. So the previous slide I shown, the same way we able to demonstrate, losing an SSD, the rebuild performance is much higher than their baseline, currently what they're supporting. So this is kind of helped them to now to go. Another thing is, if they've seen this, if you're seeing here in the 15 terabyte, if you do a basic math, 15 terabyte into 2, it should be 30 plus terabyte, right? But they're using only on 21 terabyte. The reason is they wanted to not to go beyond 75% of the capacity of the SSD, because they want to make sure that beyond 70% they have seen some performance degradation. So that is where we said, so using our product, the fact that how we do the data shaping, data sequentialization, data compression, the drop in performance, even if you go from 70% up to 95%, there is no drop in performance. You got a linear performance, sustained performance throughout up to 95% of the SSD utilization. So combining the benefit of the data compression, data sequentialization, and using the full capacity utilization, they're able to increase from 21 terabyte to 66 terabyte. So that what does it mean for MariaDB instances? I'll talk about that in the next slide. And more importantly, the blast radius is reduced. Instead of going from all the users, at the storage, losing an SSD, having entire users to be, even they have a good fault domain on the database tier, but because of the storage issues, the blast radius is significantly reduced within that particular primary instance itself. So here is the high-level picture of how we kind of help them at the rack level design. So they have a same, as you see, the 15 terabyte. They were supporting 15 user MariaDB instances with 21 terabyte of thing. So they are around 10,000 servers. Even if you account for a 2% of failures over a year, will trigger 600,000 of failure from a primary to the. So this is what it was happening. And with us, with using this, they're able to increase the storage density from 21 terabyte into 60, and the user instances has increased from 15 to 20 user instances. And with that, the 3.2x higher capacity. And what does it mean in terms of the dollar is like 58% reduction in the TCO per terabyte is a dollar per terabyte. And we eliminated complete zero, zero failures from the primary into this. So that is a significant benefit. And the fact that they able to increase the MariaDB instances from 15 to 20, there is a 33% higher multi-tenancy benefits they are able to retain. Of course, the last point is on the customer satisfaction, because there is no delays in the users failing out from the primary to the DR data centers. The customer experience has improved tremendously. So that's another point they really like about our product. The same thing we are able to, wanted to test this now with the MySQL. Wanted to make sure, so given the MySQL environment, here we had one more customer. It's not completely. We are still a work in progress. I would say premier. I would say POC scenario, where this customer they want a higher resiliency than even a single SSD failure. So what does it mean is they do not have, if I lose an SSD, because they do not have a dedicated IT admin team which will take care of, replacing this SSD on the time. So they wanted an additional level of resiliency within the system. So this is where we kind of provided, we provide something called a VHC, virtual hard capacity. So what does it mean is that you can provide one more SSD within the RAID group. So we will take care of having that as a hot spare or a hot, but it is part of this one. It will help to increase the performance, but it also increases the resiliency. What does it happen is, if you lose an SSD, we'll operate at a little bit of a lower performance, this one, but we don't need to replace any drive failure. Then we can tolerate one more SSD failure. So that means you can have two sequential SSD failures. Thereby, if you're seeing probably in the, large data centers like Google's or any of the Facebook and those things, so they will go, an IT admin go at a specific times to go replace these faulty SSDs. So those kind of customers, where you have this, wanted a higher resiliency than the single SSD failure without drop in performance. This is of significant benefit that we are working with one hyperscalers who has a similar requirement. So here, the same thing, as you see in the previous slide, we had a virtual hard capacity has been allocated, and here we pulled out an SSD, and we wanted to see the virtual hard capacity is turning to 0 because this is becoming a failed drive, and whatever the virtual hard capacity is become a part of the working device. So this way, and the rebuild will start working behind the scenes here, and again, as illustrated with so with all working, the performance is at 2.5x. This is, an additional SSD provides a marginal improvement in performance, but it is more designed for increasing the resiliency rather than boosting the performance in a far better, right? So this is more for the resiliency factor. And when we lose an SSD, even the performance compared to the baseline is 2x higher. That means you get the much 2x higher performance with the higher resiliency using the VHC counts. The fact how we operate is because we have a distributed parity. We will take care of striping all the parity across all the available storage devices. We create an array out of that, and then there is when you enable the VHC virtual hard capacity, that gets distributed as well. So I'm losing an SSD here. If you see here, so that virtual hard capacity is moved, disappears, and becomes exposed to as a user capacity. So that thereby there is no drop in user capacity, losing an SSD or this one. So if you lose one more subsequent SSD, here in this case, the parity will disappear. That means when we will reduce to the RAID 0. So losing in one SSD will reduce from a VHC setup, go into this mode. Further losing an SSD will go into the RAID 0. So that's how we kind of increase the resiliency. And another important factor I want to highlight here, compared to the traditional RAID, when you're losing an SSD means you have to rebuild the entire capacity. capacity is completely, it doesn't matter whether you do what is being allocated, how much being used. But in our case, because we have a metadata of all the data that is being written into that is coming from the application, MariaDB or MySQL, we have a complete metadata information is stored. We know how much capacity you're storing, and only that much amount of capacity will go on rebuild. Thereby, we'll improve the rebuild performance, the rebuild duration much quicker compared to the traditional RAID methods that you are using in case of rebuild. So these are the ways we kind of improve the resiliency, faster rebuilds. The other important factor is on the RAID amplification. So if you are not familiar with the RAID amplification, is like, in the case, the difference of writes that come from an application, which could be any database application or any other application. What it writes to an application to what the eventual SSD sees is a lot different. There is an additional amount of writes it has to incur. So, for example, just to say that, since I was, so Facebook, Twitter, or any of these social media companies, they process hundreds of, the billions of small object sizes, like the things that you like, the thing that you comment, or this thing, which could be as small as 100 bytes. But behind the scenes in the SSD, the indirection unit is 4K. So you're writing at 100 bytes, right? This here is a 4K block, so 40x kind of a write amplification. So when we tested this on the MySQL application, here as you see here, the baseline is around 2x write amplification.
Question.
Sure.
Would it make sense to batch all that information instead of writing individually?
Absolutely. That is what we do, the data sequentialization.
But Twitter is not doing it in their own application?
They do. The Facebook does. They use a RocksDB, which abstracts something similar. But what we do is a much extended version of that. So the RocksDB uses a LSM tree architecture. Then when you write this, so there is a compaction process kicks in. So what we do the same, much more enhanced. We separate the keys and values, and this RocksDB running on it. We do a 100% compliant RocksDB compliant key value. By the way, behind the scenes, this is a key value storage engine. That's where we are able to know what the keys are coming from the application, how much we need to do the data sequentialization when we wrote exactly that does same. So to answer your question, they do it, but again, actually not in this slide. Yesterday I presented a slide where we kind of compared to the RocksDB. Maybe I can pull this presentation. So if RocksDB does a 22K operations per second, we shown that same performance can boost it up to 140K operations per second. So that is 7x performance boost, even with the RocksDB enabled applications. Yeah, so I walked through that thing yesterday in the other session, how we are kind of helping to this one. So because we understand, so the thing is, there is a B tree. All the traditional databases uses a B tree, and then there came the era of the LSM, which kind of vastly minimized the impact of the performance and the write performance rate amplification. And we are taking it to the next step of taking it further. And here, the other factor I wanted to highlight, I don't know whether it will capture here, is because we offload this data compression and data processing and everything into data accelerator, under our product, the CPU utilization savings is significant. Yesterday's in MongoDB session that I was doing, whether you do a data ingestion or mixed workload or a read-only workload, the CPU savings from that is around 8 to 10%. But if you consider the performance per core, that is almost 2x higher. So what you can do in 20 core machine using, like MongoDB uses a wire taker, that we can do it in a 10 core machine. So that's a phenomenal CPU saving. Then you multiply by 100 servers, how much of CPU cores are, could think about. So that's, so other factor, for us, this I want to relate to one customer, CDN, content distributed network we are working on. So they use this edge server, and they have 10 SSDs in a single server. and they use a high performance TLC SSD. And what we are able to demonstrate is they can reduce that the 10 SSDs into 8 SSDs, moving from a high performance TLC SSDs to QLC SSD. The dollar per terabyte on a TLC SSD $132, and on a QLC is $98. So there is a flat per SSD is $32 per terabyte, and you multiply by 40 this one. So 40 terabyte per server multiplied by 30,000 servers they have it. So the total, just on reducing this rate amplification, the savings around 7 million. So there is a, because the SSD flash works on the program error cycle, the more you write, the faster you will, retire. So if you expect this for a 3 years, the faster data ingestion, write amplification, all these things will reduce this, the lifespan from 3 years to a year and a half or even 1 year. So you got to go and, re-provision or purchase or incur a capital cost to get that additional SSDs to run it for 3 years. Hyperscalers typically use those things for 7 years. Microsoft and majority of the people, they use it for 7 years. So typical enterprise customers that have come from work with this one, they use it for 5 years. And very rare they'll use it for 3 years, because 3 years you don't want to replace every 3 years. So 5 years or 7 years. So this is where we help the longevity of the SSDs to run it. If you're using for 3 years, run it for 5 years or 7 years. So using whether using MariaDB or MySQL, building a resilient applications, we kind of improve on making your primary instance to be more fault tolerant. Thereby, you have the primary instances to be, highly resilient to any of the failures within the storage infrastructure. And thereby, we also improve, because the fact that we do an inline data compression, this, when it gets replicated from the primary to onto the secondary, here we take care of applying these logs, which is happening on the primary, which is what is generated in the MariaDB binary log, gets replicated onto the secondary. The fact that we apply this into a faster, there is also we kind of improving both the recovery time objective and the recovery point objective. So this is a high-level comparison. If you use a RAID 0, you don't get a data protection, but you get a performance, and you got to also get a higher capacity. But if you use a RAID 10, you get data protection, but performance, because if you have a RAID 10 4 SSDs, the write performance split by half. So you lose the 50% of the performance. This is where we kind of provide the performance protection, and performance during the rebuild also immensely significant. Of course, the cost. So this is somebody is coming. This is I've presented at another storage conference. They've asked a lot of questions at the core storage level. I have a lot of RAID. I've used hardware RAID. So how does it look? So just to put this right. So if you're using any of the hardware RAID, we are compared using an existing hardware RAID that's used in the majority of the data centers. The performance here, using it just on the pure workload, we are accelerating around 11x performance boost. So if you do is let's say around 500 MB per second, we're kind of running at 6 GB per second. And the same way for the random write, and the total, when you combine these two, the averages is to 11x. And here with the virtual hard spare, the performance increases the benefit. So the RAID, any of the hardware RAID you use, they also provide a hard spare that will be used for increasing the resiliency. If you have that kind of scenarios, the performance difference in this case is 12x. Again, this is a little high level, these additional details on what happens in performance during the rebuild, right? In the sense, the hardware RAID also provide a resiliency because it can tolerate this, but performance during the rebuild, this is where, if you have any quality of service, SLS, this is where we kind of help to provide even performance during the rebuild compared to the hardware RAID, that typically used in the data center, the performance difference is 12x. The normal operation is 11x. The performance during the rebuild is 12x improvement. And what even more important is the fact that we tap into the virtual hard capacity benefit of using the hot spare. The benefit here increases from 12x to 23x. So depending upon what's the resiliency requirements you have, based on that we will improve the performance benefit from 11x to 23x performance boost, even during the performance during the rebuild. This is the last customer scenario. I'll talk through it quickly. This is one of the largest hyperscaler in the China. So they have this EBS, elastic block storage equivalent, set up in this. So for them, the thing is their goal is to, because their EBS storage is growing faster than they could able to add their new racks and right. So but at the same time they can't keep on adding the rack. Their objective was to how do we grow our footprint and keeping at lowering our cost so that way we can economically grow our footprint. So what they were trying to do from an innovation and re-engineering perspective is so how can we tap into high density capacity SSDs, which is at a lower cost, which is a QLC SSD. So right now, this is the current deployment where they had a 10+2 configuration using the cluster. Yeah. So at the server, they have a 10 servers for the data and 2 servers for the erasure coding. So that means 2 servers can tolerate up to 2 servers can tolerate any of server failures and those things. That's a 20% of the overall tolerance rate, which is pretty aggressive. This customer has went to the very far extent of minimizing the cost and putting an increased what do you call that, a very aggressive tolerance rate. And but at the SSD level, they had each server had a 24 SSDs, a total aggregation of 2264. That means two servers, each one is 24. That is 48 SSDs can tolerate, provides the resiliency for the 264. That's if you do this one, it's a 17%. So the server resiliency is around 20%. The SSD resiliency is 17%. So anything which beats this, that means they will have any SSD, losing an SSD, even though they are using a 100 gig NIC, which is a high performance, 100 gig NIC gets you 12.5 GB of throughput. So losing an SSD, that means all the traffic has to go from a east-west within the 12 servers. So that is a significant performance impact, and that has a quality of service impact. They have the 99.99% of the SLAs that they have provided to customer, and they have to think about network provision or provisioning, CPU or provisioning. So this is any of those things doesn't meet, then they have to provide an SLA to the customer. The cloud credits to the customer. So what we provided is a layer in between these and SSD, right? So what we provide is each of these Pliops card can take up 8 SSDs. So the 24 SSD, that means 3 Pliops card, and each Pliops card can tolerate 1 SSD failure. So what does it mean is we add an additional layer of a tolerance or a resiliency within this architecture. That means that we can tolerate up to 14% of additional SSD failure. So this 17% will not kick in unless this 14% is being taken care. So what does it mean is there is no east-west traffic happens at all when you lose an SSD. So when there is no east-west traffic, only the rebuild happens within the server. There is no, the east-west traffic. That means all the 11 servers will be running a full throttle mode or full performance mode. The rebuild only happens in the self-contained. So that's the blast radius from this topic, right? How do we minimize the blast radius instead of rebuilding everything 12 servers versus containing into one server? And the fact that we rebuild faster and the performance during the rebuild is much faster. So that's where they're able to meet the performance SLAs. And the fact that we enable this into using a low performance QLC SSD, which they get the density increasing from 7.68 terabyte to 15.36 terabyte per SSD. The node density went from up to 384 terabyte. So that means they double the capacity of node density, keeping the same what do you call the cost, and improving maintaining the performance what they're able to accomplish in the previous this one. In fact, this performance is a little higher than that of the previous this one. So they are able to accomplish that the node density, lower cost, and more or less higher, more performance or equivalent or higher performance than of the existing system. So these benefits, when you are looking at a hyperscaler level, right? So this runs into, okay, anyhow, I have a dollar, this one on top. So, so what does it mean is, okay, this was an existing scenario, and this has become the Pliops, with the Pliops architecture. So improved data throughput, quality of service, and there is no CPU because there is no, all the servers doesn't need to use the CPU. So that is being immensely reduced. And the fact that we improved the availability of these distributed storage, and we added a FTT of failure to tolerance rate with additional layer of resiliency. So that's another. So this is again looking at this at a higher level. So I'm not putting the dollar number how much they are saving here, but the key point I wanted to highlight is you saw one customer with a SaaS here infrastructure using a distributed storage. The capacity has increased from 1.5 petabyte per storage pod to 5.4 petabyte. So that means they 3 times the capacity that they can store in the same storage footprint. What does it mean in terms of the dollar? Is like so 66% TCO per terabyte. That means per terabyte they reduce, if they are spending, let's say, $1,000, they are now reducing it to $44. So 66% of the dollar savings. And more importantly, so any of the SSD failures will contain this into particular server. So thereby there is no east-west traffic. So of course, like US, China is also in big time into the carbon footprint. They have just like this 10Q reports or 10K reports, they have also need to publish their carbon footprint, how much they're consuming. So that is immensely, we are kind of helping them to immensely benefit from that. So here is, high level, like, for not comparing any application, like, how can we increase in SSD capacity just by switching from from a left side scenario with the RAID 10 with the 8 SSDs with providing a data compression. Sorry.
Are you specifically optimized for database workloads or just any generic data workloads?
We operate in 2 modes. One is called block mode. That is any database, any application, software-defined storage, any application works out of the box, right? You plug in, you see the data compression, data sequentialization, right, application reduction, all these things works out of the box. But we also have one more method called key value interface mode. There, for example, Redis uses the RocksDB, right? So integrating that, this, if you see a 2x, 3x performance boost, there you see 7 to 10x performance boost. So depending upon the use case, like other customer scenario, we have 2 modes of operating, and
so generic mode and optimized mode.
Correct. Yeah, so what kind of interface you want to expose? You want to see instant results, go block mode. You say, I want to see totally dramatic results, like because I want to, improve my performance by 10x or reduce my infrastructure cost by 10x. Any of those things, then the key value interface will work. So yeah, this is another chart to illustrate how do we expand the capacity, not changing anything from the infrastructure, from providing a inline data compression and transferring from a RAID 10. Still, you get the same resiliency. Losing an SSD will not an impact. And if you are using only 75% of your SSD capacity, because the remaining 25%, you may think that it will impact the performance. We'll make sure that it runs up to native. So just changing from a left hand, right hand, inline compression, SSD switching from RAID 10 to RAID 5, and increasing the drive utilization, you get 6.6x higher capacity. Of course, you can easily attach a dollar per terabyte number here from 10 terabyte, 10.7 terabyte to 67 terabyte. How much? Not changing anything, just plug in card, you can expose 6x higher capacity. So at a high level, this is like, if you are running into...
Sorry, you were saying higher capacity or higher throughput?
Higher throughput is automatic, but if you, capacity is also, as I said, if you want to tap into the data compression, full drive utilization.
Capacity is 6x?
Yeah, you can go up to 6x, yes.
Up to 6x.
If you are not using a compression on right now, again, if you are using a compression, and you're taxing some CPU cycles on it, so you feel that I want to get back my CPU cycles, let your product takes care of the compression, then we can offload all the compression from the CPU to our card. So that means you gain the CPU cycles, whatever the compression you have, doing it on the same software-based compression, you get even a higher compression. I did yesterday talk comparing MongoDB software, the snappy compression. By default, it uses snappy compression. It was doing up to 2.5, and the maximum we saw around 2.6. That we increased up to 2.8 to 4x compression. So you get a higher compression. That means automatically more capacity that you can store. At the same time, you get more CPU cycle back to your application, so that way you can use it for any of the. So depending on how we want to reap the benefits or what's this one, that's we could help out there.
But you can't get this in the generic hyperscale cloud, right? It has to be your own data center or.
This is our product is you can plug it into any server.
Right. But I can't go to Amazon and say I want to have this kind of.
We are going to make that happen soon. We are starting with a cloud service, right? If you want to test our product, we are going to be enabling on a cloud service model, so there you bring your data, run it, test it, and experience it. And then if you want to think about putting that into their cloud service, we are making that happen. It's coming soon.
So what is the compression algorithm you're using? Is that also configurable or as a dial down observation on what it does?
We use LZ4 and we have the ZSTD as well. Depending on this one, we support both. But LZ4 is you get some compression. ZSTD gets a higher compression. What do you want? It's based on the higher compression you want to gain versus the performance. There is some trade-off. So based on that, we will support both. So you use particular compression right now?
Yeah, I'm just curious, what a compression ratio when you say, okay, I'm just wondering if it comes as a source of different compression.
Yeah, right. Yeah, the next generation product, some of the feedback that we received from the customers that they want to, maybe I'll not say, reveal this one. So one of the database vendor is looking to offload all their database backups into our product, so that way the moment you plug in our product, automatically detect, and when you're running a database backup, it offloads to that. So thereby, you're on your host system where you're running the database, there is no CPU cycles, because when you're running any database compression, database backup with a compression enabled, there is a significant amount of CPU. Just to put that into perspective, 30% of CPU, if it uses 30% of the CPU when you're running a backup, that reduces to less than 1% of the CPU. So with the same duration, backup duration, you reduce the CPU cycle from 30% to 1%, less than 1%. So because we take care of that.
So
You can use that.
So I would assume you have dedicated kind of hardware chips taking care of those compression.
Yes, absolutely.
But that is kind of optimized specifically for compression.
I mean, this is a compression is a part. Okay, maybe I should have had my this one. See, yeah. So compression is a part of that, right? Like again, like every data that comes in, we will make sure that it compresses, indexes, sorted. It's a completely a key-value storage engine. We know what every data, whether it's a data or metadata or everything, we compress it in a line, right? And we also index it like, so that the next time application request, we know exactly where we have stored the LBS, logical block sequence numbers of the SSD. So we fetch it faster. So that's how we are kind of accelerating.
Your product space, do you classify yourself as a DPU or just as an intelligent storage?
Yeah, the name is Extreme Data Processor, right? Like, so this is put in under multiple dates, somebody at SmartNIC and somebody at a DPU. But we had an interesting demo we did last year at the Flash Memory Summit, where we have demonstrated running a database application completely without no Xeon, Intel Xeon thing, running a DPU and with the Pliops. So the DPU is running all the data processing and everything, providing all the storage, offloading the storage processing to our product. So we complement the DPU in that way, depending upon what the use case like, and somebody want to put it under the Gartner, put it under the SmartNIC, which is not this one. But yeah, so that's how we could classify it. Yeah, maybe easy answer is we want to classify under any data processing engine, right? Like data processing storage engines. That's where we. So all the future product announcements, everything, we want to go up to the application, provide the value chain. Value benefit to the database, big data, or analytics application, or even to the software-defined storage application. So that's we are already doing it, but we want to increase up the next gen product. You have a analytics offload also coming into the picture. So yeah, so if you are trying to adopt a high density SSDs and lower the cost and minimize the blast radius, we kind of provide that all those benefits, right? Like and more importantly, there is no performance drop during losing an SSD. The performance drop is very minimal, and the rebuild cycles is very absolutely faster. And we provide a provide a knobs for based on customer needs to tune into that. With that, thank you for your taking time and done with your presentation. Thank you.